Okay, so what is Genius? If you see, Genius is an offset 1 project in OpenDaylight. By saying offset 1, meaning it's kind of using core kernel OpenDaylight components, and it provides services to that's okay, and it provides services to application modules. It's essentially a framework to support service integration and application coexistence. The next major function of this Genius is decouples the southbound plugins from the northbound application modules. So the application modules, without bothering about the southbound plugins, they can interact only with Genius and do their work. Further, Genius has the ability to add new southbound renders. So today we have, say, OpenFlow plugin renderer or OVSDB renderer. If there is a new southbound node, we can actually create a renderer and attach it with Genius, so that the Genius interface, northbound interface, remains the same, and internally the Genius hides the communication with the southbound plugins. Then it allows resource sharing. So considering several different applications developed independently, they might be using the same resource IDs or resource numbers, and when they work together, they may end up writing to each other tables or groups. So Genius also facilitates this resource sharing, so that like different application can work together in an interference-free manner. Then since it's a new project, it's introduced in last Boron cycle, but this is not a new code base as such, because most of these components are coming from our parent project, that is VPN service, and there we were using these modules. When we get to know the discussions around application coexistence, and we noticed that our VPN service project already has these components that can greatly help in application coexistence, and that's how we this Genius project came into being. So let's see the Genius components. So Genius, there are several Genius components. Mainly you can find two different categories of Genius components. The first category is where the modules that are actually helping in application coexistence, and the second category is where the Genius components are providing common utility services that every module can use to avoid duplication of code. And there can be several common functions that every different project or application is doing, and we are putting all those kind of utilities in one place, so that different applications working together on top of Genius framework can use those services. So in the first category, where we talk about like modules helping in application coexistence or service integration, we have our major component, that is interface manager. Interface manager basically provides a logical view of the networking endpoints, and it provides an ability to create logical interfaces. And once the interfaces are defined, the services can actually bind to these interfaces to pull the packets from these interfaces and do their work. So this is the major component that helps in service integration. Then we have overlay tunnel manager. Overlay tunnel manager provides the tunneling capability, so you can create different. We'll discuss in details about these components. Then we have the resource manager. I talked about resource allocation. Using the resource manager, different application can allocate OpenFlow resources in an interference-free manner and utilize these resources while running together. Then the next module in the utility section, we have our ID manager module that generates unique integer IDs. So you can provide a specific key, and ID manager will generate unique integer ID or for that key. And these IDs are persisted across the cluster restart, so that like whenever you query for an ID for a particular key, you will always get that integer ID. Then we have MDSAL utils module. MDSAL utils basically provides an interface to all the MDSAL related interactions, be it if you want to access some MDSAL data store, you want to read, write, those kind of methods are there. If you want to interact with OpenFlow plugin constructs, so these all interactions are, MDSAL provides a very common, generic, and simple API interface that modules can use to interact with MDSAL. Then we have an FCAPS framework and application. So FCAP framework this provides a mechanism with which like different application can gather the FCAPS information, and you can collect it one place, and then for higher layer modules can subscribe to this data through the FCAPS framework and fetch that data. So different modules generating this FCAPS data, and FCAPS framework manages that data so that different applications can register and fetch that data from this FCAPS framework in ODL. Let's see application coexistence. So during the beryllium or boron time frame, when there were several different applications developed in OpenDaylight, and they felt the need to work together, and they started integrating these two services. They started facing these kind of problems, and the very first problem was partitioning of OpenFlow resources. What happened that these different applications were developed independently, and all these applications are using the same IDs or the table numbers or the group IDs, and when these two applications are working together, they are actually stepping on each other's resources. So there was a problem like how you can allocate or assign a set of resources to one application so that it is not used by other application. So this problem of resource sharing was the biggest problem in the beginning, and our resource manager framework that Genius provides that solved this problem. Then second problem was the demultiplexing. So all the packets that are entering, they are coming into table 0. And if there are multiple services or multiple applications interested in the same packet, each application is writing in table 0 to fetch the packet towards their pipeline. And then there was a problem like who gets the packet first, and after that, how the packet is delivered to the next service. So again, as I explained, our interface manager service with service binding capabilities easily solves this problem, where you can create one interface, you can bind several different services, and interface manager takes care of distributing packets to different services based on defined priorities. Then in the data plane, so this is more like hiding the southbound abstraction, where different services are only talking to interface manager without bothering how the southbound is handled by the Genius modules, and they can only look into the interfaces, and each service can only care about the interfaces that they are interested in, and they can talk to Genius about those interfaces. Okay, so let's see what happens in the data plane. So in the data plane, say the very first our table 0, that is classifier table, where packets are classified belonging to a particular interface. So the service modules or the applications can create one interface with defining the classification parameters. The interface manager in Genius actually owns and programs this table 0 with those classification parameters. And once the packet is classified belonging to a particular interface, the interface manager or table 0 associates data plane ID with that particular packet. And further on, that data plane ID, that is the interface index, that will be used to identify the interface that packet belongs to. Now, after that, the packet is fed to our service dispatcher table. So this service dispatcher table is doing the arbitration for packet to be delivered to different services. On one interface, different services can bind, and for each service bind, this service dispatcher table will contain one entry, so that on the basis of the priority, the packet is classified with this dispatcher table identifies which service this packet should be fed next. Once one particular service pipeline processes that, and if it is not able to consume that packet, by consuming it means like whether the first service drops the packet or forwards the packet, it means the consumed. If not, if the service the packet needs further processing, the service 1 will feed the packet back to dispatcher table, and dispatcher table will select the next service and feed the packet to the next service. And this happens with all the services bind based on the priority. With a similar concept is applied at the egress also. So whenever a packet is like destined to a particular egress interface, again services can bind egress at the egress, so that when the packet is actually going out of a particular interface, the packet is given to the service. For example, like currently the ACL services are using this, so you want to apply some rule or some filter on the egress also, so that can be used, our egress service binding can be used. So this is getting a little into detail. That's what I explained about the interface manager. That interface manager actually owns the table 0 or the classification table. It does the classification based on the interface classification parameters defined. And with the interface manager, you can create a hierarchy of interfaces, so that like you can define granular interfaces. One OF port belongs to one interface you can create for a particular OF port. And if that OF port is having multiple VLANs, you can create different granular interfaces per VLAN, and you can bind services with finer granularity there. Then the next is service bind. As explained, you can bind multiple services to one interface, and the interface manager will take care of delivering packets to these services bind based on the priority. The final is that like it hides the southbound layer, like southbound plugin or whatever the protocol we are using in the southbound. So applications are only looking into the interfaces. Interfaces are the service endpoints, and they are applying services to those interfaces. They are not, applications are not bothered about like how these interfaces are realized in actual data plane. This slide explains like how you defined interfaces with the interface manager. So we have a YANG-based API where you can define different classification parameter for a particular interface. Currently we have like VLAN kind of interfaces, and also we can create a tunnel interfaces like VXLAN and GRE. This uses the IETF interfaces data model as the base, and we have added additional augmentation on that IETF interfaces data models to realize further granularity and define the further classification parameters. As explained earlier, you can create a different kind of hierarchies of interfaces, so that the application can use fine-grained interfaces or fine-grained classification of a particular packet. This slide explains how the service binding works. So in the table 0, when the packet is classified, we associate two fields in metadata. First field is the service index that identifies like where this packet is going to, which service it is going to delivered first. And the second is the interface index, that is the data plane ID for the particular interface. So these two entities or these two fields are added to the metadata, and the packet is fed to the dispatcher table. dispatcher table actually matches on interface in so if you are binding two different services, you will have two different entries or n different entries with the same interface index but different service IDs, and these service IDs are based on the priority given while binding the service to an interface. So you can see these are the parameters that you provide when you want to bind to an interface. You provide the service priority, the service type, and then the service info. And if you look at the service info is basically the OpenFlow rules, where rules and instructions that you can provide. And when the entry is added in the dispatcher table, the dispatcher table matches with the interface ID and the service index, and it actually applies the provided OpenFlow rules while service binding. So whatever actions services has given, it simply applies those actions. In most of the cases, these actions are go to a particular table to fetch the packet to a particular service specific table, and from there on the services take. So this is how service binding works. Then we have our ID manager service. ID manager is a core utility module. Actually, in several places we need to use integer IDs, and we want them to be unique IDs. For example, say if you are, one example I talked about the data plane interface ID, and we want to have a unique ID for each interface, and other several places wherever you need integer ID, unique integer IDs, you can use our ID manager service. And with ID manager service, you can create a pool of IDs giving the start and end, and then services can request individual or a set of IDs giving a particular key. So say you have created a pool of IDs for interface index, and whenever I want to get an interface index, I will request ID manager giving the control plane ID of the interface, and it will generate the data plane ID. And that ID I will use in the data plane or wherever I want. These IDs will be persisted with ID manager, so that whenever the controller restarts and a module tries to get, it will get the same ID every time. That's how you can keep your data plane intact. So whatever IDs you are using in data plane, that will never change with a controller restart or any change in the controller. Then we have our resource manager service. Resource manager, I explained, like facilitates resource allocation to different services or applications. It is essentially based on ID manager service. So what it does actually, for different kind of OpenFlow resources, be it table IDs or group IDs or meters, the resource manager actually creates different pools for these resources. And whenever a service request for a particular resource, or say for example some service wants us to use 10 tables, it will simply request 10 tables from resource manager. Resource manager in turns request ID manager to get 10 IDs from table ID pool, and it returns those IDs to the application. And that's why you say, if different applications are requesting for these resources, they will always get a different set of resources. So they do not need to bother about, like, if they are using some table ID or some resource that is already used by some other service. So this is how the resource manager works that I explained. So resource manager actually, there is an initial config where you define the pool config. Different we have internally defined table ID pool. You can have, like, interface manager actually reserves some initial table IDs like table 0, table 10. These we are using for our classification. So these will not be actually given to any service or application module. And with this range, we create these table ID or resource ID pools in ID manager, and whenever a service requests, we'll deliver the requested IDs. Then we have our overlay tunnel manager. So as we heard that, like with interface manager, we can create tunnel interfaces. For example, VXLAN, GRE, or VXLAN GP, MPLS over GRE, these kind of tunnels we can create. So our tunnel manager basically facilitates this tunnel creation. You can, with the tunnel manager, you can define a transport zone, and in a particular transport zone, you can add several transport endpoints. The moment you add a transport endpoint in a particular transport zone, the tunnel manager automatically creates a bidirectional transport mesh between all the transport or tunnel endpoints that is defined for a particular transport zone. So for example, if a service wants to use a VXLAN tunnel transport, and he knows like on what devices it has got the tunnel endpoints, it will create a transport zone with type VXLAN, and all those transport tunnel endpoints will be added to the transport zone. And the moment a transport zone is added to tunnel endpoint is added to a transport zone, the tunnel manager automatically creates a corresponding tunnel interface and manages those tunnel interfaces. So services can query that give me a tunnel between these two endpoints, and the tunnel manager will return the corresponding interface. Services can go and bind services to it and pull the packet from that tunnel. So currently we support VXLAN, GRE, VXLAN GP, and MPLS over GRE tunnels, and we provide tunnel monitoring using BFD and LLDP. Since the LLDP monitoring involves the controller in between, that is not a preferred way. So largely we are using BFD for tunnel monitoring. However, LLDP monitoring can also be enabled if required, if BFD is not there. So it also generates tunnel up-down events. So whenever there is communication break between two endpoints, either the BFD or the port status will tell that this tunnel is not operational, and in the interface manager, this tunnel's operational state will be set to down, and seeing that, the tunnel manager generates a tunnel down notification that different applications or services can listen to and take appropriate action. This slide explains how we can plug in different southbound renders. So we have in interface manager, you can see there are three parts. Mainly the first part, the northbound API or the interface manager data stores, where you can configure a particular interface and provide the service bindings. The second part is the interface manager listeners. Listeners actually listen to these data store changes and take appropriate action. And the third part is southbound renders. So if you see, the southbound renders are actually decoupled from the listeners or the API part. So if required, you can if the, for example, right now we have our OBSDB renderer or OpenFlow renderer. If there is a different southbound protocol, you can simply create a southbound renderer here and attach to the listener interfaces. So once you do that, you see the northbound interface does not change. So applications who are using these interfaces, they will not need any change, and they will be able to work with a new type of southbound protocol. Putting it together is the same pipeline I explained earlier. So this is the actual example. This is the so currently ODL network is using Genius framework. We have our SFC module also trying to integrate or utilize Genius, and we are also discussing with GBP to integrate with Genius. But currently in our last release, Network was the only candidate who was using the Genius services, and here you can say within the network itself there are several different services that are actually working together on Genius platform. You can see the different colors actually define one particular service, and this dispatcher is actually delivering packets to different services, and at the end of a particular service, if the packet is not consumed, you see the packet is sent back to the dispatcher again, and dispatcher further delivers packet to the next service. And at the end you can see the example of egress service binding, where we are binding ACL services at the egress interfaces. That's all from my side. I'll give the dash to Faseela and team for the demo and the workshop, and we'll see how we can create interfaces with Genius, and how we can bind services, and one live example where you will be able to create interfaces, bind services, and see it actually working. Thanks. Yeah, sure. Preference would be based on the service priority. So whenever you bind, yeah. No. It's not that way. It's not that way. So you bind services with a specific priority. Certainly these services must be agreed between the services working together. And what happens, the dispatcher will deliver the packet first with the highest priority. Once that particular service acts upon that particular packet, after that it actually sends the packet back to dispatcher, and the dispatcher selects the next service in the priority, and packet is fed to the next service. So it's a chain of services being applied on one packet. Every time the packet is sent back to the dispatcher selects the next service and feeds the packet to the next service.
So if there are 5-6 actions to be done on the same packet, those actions will become a service.
You have entire pipeline. A service can have multiple tables. Each table can have different entries. So the dispatcher will only deliver the packet. So normally it's not delivered. You can also specify some action to be taken there at dispatcher itself. Then you can simply say at the service bind route, classify and send the packet out to this port. That also you can do. But normally it's not only that simple. So every service has several hops to go, several tables to consult and go through. So what these service bind actions are normally is go to my service entry table. So first they fetch the packet to their domain or their service pipeline, and then their service pipeline like whatever they want. Okay. So the flexibility is there. The service binding action can be anything. You can define, okay, go to out or drop the packet or pull the packet to a particular pipeline so that it is processed further and sent back.
This is kind of forwarding here.
Kind of, you can say. Yeah. No. Why would you do that? Okay, so there is no as such restriction. Right now we can have 16 services. If you have like, if you are saying example that one service can be active at a time, right? And you want to reuse the same service ID or service priority, in place I will say use two different service priorities. It is always possible that there is a gap in the service priority that you give. So at one point of time, there will be three services active, one with priority 1, the second with 4, and the third with 5. So gap is possible. So you can use the range. You do not want where two services are actually containing or fighting for one packet at the same time. right? So you have flexibility. So if you want to use two services at the same priority, I'll say okay, give two different IDs and give it. If this is not active, next service will be this. If this is not active, no, that is no. At the same time, it will go to no, that's not possible. Yeah. Yeah. No. Then you are asking for packet replication. That's not the agreement, right? That you can do at some point in some group, but not here. Yeah. Right. Yeah. That's what I'm saying. So if you have Genius framework, you see one service GDP that gets the packet first, does the classification, put something in the metadata or does something in the packet, and then the next service will be your SSL. So that's how you can chain different services within one domain, right? But previously it processed one, and then that particular service was feeding directly to the next service. Here you have the flexibility, the same thing like you have a fixed binding that after this service you are going to this service. Here you have the flexibility, you can deliver packet back to the dispatcher will send to the next service. And you can, in one solution, you can have different services being active and doing their work. So that's what we are actually, right now we are discussing with GBP and SFC teams. SFC will be soon migrated, GBP in discussion. Yeah. So I hope those things will come very soon. Because see, network earlier, SFC was using some classifier from network, and now network is actually on Genius framework. So yeah. That you can do. So maybe you can utilize the metadata. So what happens, you do classification. Once you classify, give to this, and you are somewhere in your SFC you are classifying with something, like say maybe NSH or any kind of identifier that you have done. Result of your classification you can store in metadata, and the packet goes next to the SFC. Hmm. Its binding is triggered dynamically. The case what he is explaining, that it may not need, a particular packet may not need SFC, only a specific packet, or so there you have the interfaces. Then I see what the classification, because here the interface manager is also doing the classification, though that is not a very elaborate classification. So that classification, once we classify, we identify this as an interface, and then only we bind a service, particular service to that interface, right? So here in your case, classification is happening in a different service, right? So maybe right now, not at this moment, we are not allowing, but if required, we can allow to modify the interface index itself. In like you can do a second level of classification, and you can put a different interface ID on which the next services can bind. So that also we can do. I mean, you can do it right now, but as per the strategy, we say that services will not modify the interface ID. Once classification is done, you will follow that classification or that interface only. But you can also for now it will be a hack that you classify. The next level of classification is done by say policy or something, and then you modify the interface ID, and the next services will bind to that interface only, not in this interface. So that also you can do. Yeah, sure. This one? Yeah. 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 Right. Okay, well, so yeah, I understand your point, but I will say that this largely is based on the OVS, right? And this largely is working for OVS, and OVS supports resubmit, or you can with resubmit extension, Nisira resubmit extension, you can go back to lower ID. So that's what is utilized here. So with Nisira extension, resubmit extension, you can go from any table ID to any table ID. So that's what. But yes, I agree your point. If you go with pure open flow protocol, you cannot go from say this 42 to 17. You cannot go. But here we are using resubmit to 17. Yeah. Yeah.
Say like there are three controllers, so there would be a common GPS between all three, or the individual controller.
Every controller is running its own Genius instance. So it's that is one layer below, right? So Genius actually works on inventory and topology data stores. So the clustering is handled at the lower layer, and that whatever is updated in these in southbound data stores, Genius actually act to that.
Also, one more. You said about initially why Genius came up was to decouple northbound and southbound.
Yes, two major reasons why Genius was proposed. One, service integration, multiple services working on one particular interface or one particular classification or classified packet. And the second is like independence from the southbound plugins. MD-SAL actually does that, but it is even above that.
Scheduler for MPLS.
No. It's not scheduler for MD-SAL. So different kind of say when you are creating an interface or realizing, say for example, you are realizing a tunnel interface. So you talk about VXLAN tunnel, right? If you have a pure open flow switch, you need to classify on the source IP, destination IP, or other parameter in the pipeline, and then you say that okay, this is a particular interface. In OVS, you can go and directly create a tunnel interface. So these two methods are different in different southbound protocols, right? And from the interface manager view, services are only saying that okay, give me a tunnel interface with this source IP, this destination IP. How that is realized, how that is created in actual data plane, that applications are not looking into it. So that abstraction it provides. Okay, then we'll move to next section. Okay.
Hello everyone, I'm Faseela. I'm a project committer on Genius Project and working as a senior software engineer at Ericsson. So I hope it's clear on what Genius is and what abstractions it provides. Now let us have a hands-on session on how it works. So basically in this workshop, we are providing you some code in the VM whatever is already given. So the code is already having like one service is already bound. Okay, and then hello. Okay, so we have one exercise apart from that, so that you guys can write one service on your own and then see how these two services are coexisting without any issues, and how the packets are dispatched from one service to the other in order, in the priority order, without any issues, and how you can see that connectivity is working fine. So the basic API is what you want to see this application coexistence working is, uh, we have this interface manager, and then we have a create interface step. That is the first thing. You can create any interface based on your requirement, a trunk interface, a trunk member interface, or a tunnel interface, etc. And then the next step will be binding your particular service to this interface. So binding the service means you have to provide the service priority. So depending upon your service priority, the pipeline will be programmed. And then the final step will be creating the service pipeline. So as you see the network, OpenDaylight network pipeline, right? There are multiple services like ACL, L3 VPN, L2 VPN, and then IPv6. So many services are bound using Genius. So these are the steps they follow. So they will have their own pipeline. That is the third step. Before they do that, for each of the interfaces on top of the ports, they configure interfaces and then bind their services with their particular priority. So the first step, what it happens is, they consult the Genius project saying, we want to introduce a new service, or we want to integrate our service to Genius. So we would like to reserve our set of table IDs, and then this is our service priority. So for example, if you see, we have ACL as the highest priority service now. So the next one is DHCP. So all services agree upon themselves on the service priorities, and that's when they start integrating. So that will be the first step. So in this VMs, whatever it's provided to you, you have a simple demo setup there. You have OVS running, and we have the mininet, and some scripts are provided. So with the script provided, you will be able to bring multiple ports and then host connected to it. And then you have a ODL controller running on the same. And then we have given a sample app code base. So that is running on top of Genius. So maybe you guys can get started with setting up the environment. I think everyone has already taken the VMs. I think almost all have already copied, right? Maybe you can just start the VMs. Oh, is it? You log in using this username and password. login done. Once you've logged in, right, you can go to the home folder. There is a tutorial folder there, and then a Genius sample app. Actually, it is a separate Maven project we have already created. So what you're going to do is, you'll develop your application code inside this repository. So we have already put the basic infrastructure in place, so that all the dependencies to various Genius features are already added in the pom.xml. So the various commands that will come handy are shown here. So the command to build the code inside Genius sample app, plus how to run the controller, and then how to start the switch using Mininet, so that you will get that topology whatever was shown in the previous slide, and the command to dump the flows. So at each step on Genius integration, we'll dump the flows and see like what are all coming on each of the steps. The VM is already having Eclipse and IntelliJ. Whatever you are comfortable with, you can start using it. And under the tutorial folder, you'll see a README file. So all steps are actually documented there. In case you have any doubts, you can just open the README and see. And you guys can import the code in IntelliJ or Eclipse, whatever it's. Parallelly, you can build the code also using that mvn clean install command. Ambient clean install command given in the PPT, right? It's minus NSU. In case you're pasting it, I think it's a mistake in the PPT. To start with the coding, right, you'll see a Genius sample app provider.java once you've imported the code in Eclipse or IntelliJ. So here if you see, we have created a okay, no, anyways they are seeing it in their laptop. On the project structure, you will see there is an API, Impel and CLI bundles we have created. On the Impel bundle, if you check the pom.xml, you will see all the dependencies to the Genius modules. We have added interface manager and the resource manager, ID manager, ITM, all required dependencies inside the Genius sample app impl module. Now to demo things easily, we have added some CLIs for this create interface, delete interface, and bind service or create service pipeline. So this is for you to try it out on your own on the CLI. And the main implementation file is this Genius sample app provider, which will have the implementation for all the APIs, create interface, bind service, and create service pipeline. So currently the whole code will be commented out. You will have to first uncomment this and build, and before that you can just see the CLIs whether it's coming up or not when you started the controller. Sample app provider can be uncommented and you can build it in one shot instead of building it one by one. In Genius sample app provider, so you need not build the whole thing, you can just build that sample app impl if you want. That PLAMD, I was just planning to show that. If you use this command ambient clean install -pl colon the bundle name space -amd, it will build that bundle along with its dependent bundles. It will not build the whole thing. Okay, so I thought once your build is done, I'll explain it. So once the build is done, you can use the create interface CLI. Create interface CLI takes as input interface name and a port name. Port name should match with the actual port name on the switch. Okay, so basically what you're saying is configure an interface with this particular name on top of this port. Okay, you can, this is just a CLI we have provided to demo the whole thing. Actually, you can specify a lot more parameters like what kind of interface you want, either a trunk interface or trunk member interface or VXLAN GRE interface, everything you can specify. No, you will do create interface only. Interface manager will internally generate a unique tag for that interface. Okay, so that is what is called interface tag. So this is basically used in the data path to identify that a packet has come on this particular interface. Okay, so the interface tag will come inside the metadata field. You will be seeing one write metadata and a tag. So that has the unique. In Genius sample app provider, we have used a data store job coordinator utility. So that is another utility provided by Genius. So what it does is, if you have multiple tasks and you want to execute them parallelly, that is, they don't have any dependency between each other, you can execute them parallelly. So for that you can use this data store job coordinator. You can enqueue a job with a particular key. If two people are queuing jobs with the same key, they will be executed sequentially. If it is different key, means they will be executed parallelly. So it improves the performance, and that way you can parallelize your operations based on your requirements. So we just wanted to show how that can be used, so we have included it in that create interface. So you're all are done with the build? Still going on? first step. It is the create interface. So first you have to start the controller and then start the switch. So once the switch is started, if you do OVS VSCTL show on the switch, you will see 6 ports there, starting with tap and some 11 characters. Now we are going to configure interfaces on top of it. So you would have seen the previous topology whatever I had given. So on OVS, suppose if you have 2 tap ports, how you can establish connectivity between these 2 ports? If there are some hosts behind them, how do you ping them? That's what we are going to do first. That is the code which is already available. So for that to work using Genius, you have to do a series of steps. That's what we are demoing now. First, you have to configure an interface on top of that tap port. So you can take 2 of the ports. We have given 11 and 12. If you see, maybe you can give the same command also. Create an interface. Give any unique name. The interface name should be unique. And then you need to give the port on which you want to configure the interface. Interface is configured, both the ingress and egress flows for that particular interface will be programmed on the switch. So table 0 will say the port number for that tap port, whatever you give, match on that port name, port number, write a unique L port tag into the metadata, and then go to table 17. Table 17 is the L port dispatcher table. Similarly, you will see another entry in table 220, which is the egress dispatcher table, that if the L port tag is coming in register 6, the output port is port 1. So basically the ingress and egress for port 1 is programmed once you do create interface on that port. Create interface is just a demo CLI whatever we have developed. That create interface, what it does internally is it writes to Genius interface config data store, which will internally program these flows. So are you seeing these flows properly on the switch? Able to see? So if you take the high level use case, right, if you use OpenStack through network, OpenStack will be doing a create port and board PM. So whenever that create port is done, internally it configures interface like this. So probably you need to create 2 interfaces. Right now you did only for one, create interface. Since you have 2 ports and you want to show the connectivity between those 2, you need to configure 2 interfaces. So you can take the 12 tap port next and configure another interface. Once the second interface is configured, you will see one more entry in table 0 and table 220 matching that particular port number. Now this is the most important step, that is the bind service. For demoing the bind service, we have another CLI called bind-service. You have to specify the interface on which you want to bind the service, and you have to give the service type and service priority. What this basically means is, one application is telling that I am interested on the packets coming on a particular port. So you are specifying a service priority. So if there are multiple applications binding on the same port with different priorities, the application whichever is having the highest priority will get the packet first. And then if there is nothing matching there, means again in table 17 it will go to the next service, and it follows like that. So currently in your code you have only one service called forward. Okay, so you can just bind service on the interface name whatever you created with the service type as forward and service priority as anything. So you can give just 5 or we have actually service priorities from 1 to 16. So you have to do the bind service for both the interfaces you have configured. The same service should be bound on both the interfaces, the same priority. Now once this step is done, you will see entries in the ingress L-port dispatcher table like this. So this means in table 17 you will be matching on the L-port tag, that is the interface tag whatever was created for that interface, and then it says go to table 30. So right now we have hard coded in our code that if it is the forwarding service, the service pipeline starts at table 30. So that is why it says go to table 30. Did you do the bind service? Okay. You have to give the same interface name what you created in the first step. Huh? Once you do it for both the interfaces, no, you will see 2 entries in table 17. Now this is the next step, creating the service pipeline. So actually whenever you have your own application, it is the application's responsibility to program this part. So currently, to show that the connectivity will work fine once the service is in place, we have just provided a simple application as part of this CLI. So whenever you create your service pipeline with the interface name, and this is the service, and you're providing a MAC address. So basically the logic whatever we have put inside the forwarding service is, whenever a packet comes for the destination, this particular MAC address, forward it on the corresponding port. We have just programmed such flows. So once you do this, create service pipeline, you should be able to do the ping. You have to do it for both the interfaces basically. If you have bound the service for 2 interfaces, do the create service pipeline also for 2 interfaces. Once that is done, you will see some flows like this in table 30. Service is being done. You can pass whatever instruction you can program in table 17. So here what we have done is we are generating a unique service tag for each service, and that is what is being set in metadata when packet comes from table 17 to that particular service. So that unique service tag is generated using ID manager. So once create service pipeline is done, you will see an entry in table 30 which says match on the service tag and the particular destination MAC. Go to that egress dispatcher table, which is table 220. And in table 220 anyways you will have an entry to egress the packet on the particular port. So once this is done, you can try that 2 host ping and see whether it's working. 0 to flood the packets, otherwise ping will not work, because anyways ARP comes with a broadcast MAC which will not match in table 30. Now these are all delete commands. I think no need to do that because it's just reverse of whatever we have done till now. Now let us go to that exercise part. So the exercise is you have to develop one more service. So just like the create service pipeline with forward, right? You just need to develop a new service with drop. Drop is the service name. So once it is done, the packets, you should see that from table 17, the packets will first go to this drop service and packets will get dropped here. Your ping should not work. Drop should be of higher priority. That's it. You will see 4 entries for each interface, and then you will have 2 service pipelines. One is for the drop service and one is for that existing forward service, and you'll see that drop service is bound with higher priority and your packets will directly go to that drop service and start getting dropped.